बिस्मिल्लाहिर्रहमानिर्रहीम। वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिजिक्स। आज हम इसका लेक्चर नंबर 16 पढ़ेंगे। लेट्स सी व्हाट वी हैव डन इन द लास्ट लेक्चर बिफोर वी स्टार्ट दिस लेक्चर। Last time we studied method of separation of variables and we applied this technique to elliptic equations. So in last two lectures basically we have applied this separation of variables technique to parabolic equations, hyperbolic equations and elliptic equations. So in last three lectures I have solved heat equation for parabolic types, wave equation as an example of hyperbolic equation, and Laplace equation as an example of elliptic equation. So we solved these three equations for different boundary and initial value problem, for different boundary and initial conditions. Today we will continue with the same method, but we will implement this to equations with more than one spatial variables. So in total we will have more than two variables. T will be there, and now x and y and z, all three can be there. So we are moving from one-dimensional partial differential equations to more than one-dimensional partial differential equations. Alright. So separation of variable techniques implemented on equations with more than two variables. So first of all, let's say I consider a vibrating rectangular membrane. If you recall, in wave equation we had a one-dimensional string and we studied the vibrations of that string in one dimension. Like it is a string vibrating up and down, so there is a displacement in y direction only. So we said if u is a displacement in y direction, it will depend on x and t. Now instead of one vibrating string, I am having a rectangular membrane where there are two directions, x and y. So any point which is moving up and down, so displacement will be in z direction, and at any point you will have x, y and t. Alright, so u will be depending on x, y, t. So you have three variables here. So more than two variables, it's a two-dimensional wave equation basically. Alright, so a vibrating rectangular membrane with negligible body force and clamped edges, fixed edges, like in the string case we fixed both edges and then studied the motion of the string. Similarly, if you have a rectangular membrane, we'll say that the edges are fixed, clamped at some place. Alright, and then you are studying the motion of the vibrating membrane. So then the equation which will satisfy the vibrations will have a second dimensional wave equation. So before we had utt is equal to c square uxx xyt plus uyy xyt from 0 to L and y from 0 to k. This is xyt, not r theta t. Alright, so see here, this is we are given boundary conditions on four edges, x at 0 and x at L, these first two conditions in blue, and then from y 0 to k, so we have conditions on 0 and k, so y 0 and y k, you also get a condition. So this is from x from 0 to L. uxy0 is equal to fxy. This is the initial condition for t is equal to 0, and because we have two time derivatives, I need one more condition on t, so ut at xy0 will be gxy. So you are getting four conditions for four spatial derivatives. Before that, in a string case, we had utt is equal to c square uxx only. But now, because it's a two-dimensional, we have x and y both directions, so uxx plus uyy. There will be Laplacian in 2D on the right-hand side. Alright? So this is your two-dimensional wave equation in a rectangular membrane. Alright, so let's see an example. Alright, let's solve that wave equation in rectangular membrane. So let's solve that wave equation in rectangular membrane. So what we have is, we have utt is equal to c square uxx plus uyy. So what we are having is, we are having a two-dimensional membrane, basically this one, all right. So we have from 0 to L, and y is from 0 to k. This is what is given. So I am given boundary conditions on this edge and this edge, x0 and y0 and yk, and this is x0 and xl. All right. So this is, so at any point your displacement up and down, right, is in the z direction, and let's call it u of x, y, and t. All right. So u depends on x, y, and t in three variables now. At any point, it depends on x, y, t. This point is of course x, y, but u will be depending on t as well. So boundary conditions are u x0, y as it is, t as it is, equal to 0, and u at lyt is equal to 0, and this is true for all y between 0 and k, and of course t positive. Other boundary conditions are u at 0 x0t is equal to 0, and the second boundary condition is xkt, y is equal to 0 and y is equal to k. x0t, x0k, 0, and of course these are true for x0 to L and t positive. And then we have initial conditions. Initial conditions are u at xy0 is equal to 0, and ut at xy0 is equal to 0. All right, and this is true for all x between 0 and L and y between 0 and k. All right, and this equation was of course true between 0 and L, y between 0 and k, and t positive. All right, so these are our domains. So this is our this is our two-dimensional wave equation in a rectangular membrane where boundary conditions are homogeneous and initial conditions are non-homogeneous. All right, so this is our problem. Now, to solve this by method of separation of variables, what we do is, because we have x, y, and t, right, u depends on x, y, t. So we assume the solution of the form S u x y t is equal to S of x y and t of t. So what we are doing is, we are trying to separate one variable first. Let's separate t first. All right, so we are separating t first. All right, if I do this, our PDE will give me, on the left hand side we have second derivative of time, so s will remain there and second derivative of time. Right hand side, c square uxx. So uxx means the derivative of s with respect to x. So I'll get sxx t as it is plus syy t as it is. I'm not using double prime for s right now. Reason is, s is still a function of two variables. So derivatives are still partial derivatives for s. All right. So here now, if I divide by c square st, we obtain t double prime over c square t is equal to, c square is gone, so I got sxx plus syy over s. This is what I'm getting. So on the left hand side you got t only, and on the right hand side you have x and y only, no t. So there is no t on the right hand side, there are no x, y on the left hand side. So again this will be equal to some constant, and I can call it, let's say, lambda. All right, minus lambda. All right, so now this first equation will give you t double prime plus c square lambda t is equal to 0, and the second equation is sxx plus syy plus lambda s equal to 0. So these are the two equations that I'll get. So here you see this is just an equation in n, and this is an ODE. But here, if you look at this one, this is still a PDE in two variables. This is still PDE in two variables. All right, so we got these two equations. One is ODE and one is PDE. So if we use boundary conditions and separate them, separate t from the boundary conditions, this is what we will get. u0 yt is equal to 0. So s x0 y as it is, t as it is equal to 0. So from here, of course, capital T at all times cannot be equal to 0. So we have to make this s at x is equal to 0 equal to 0. Similarly, u at lyt gives you s ly equal to 0, and other two boundary conditions on y equal to 0 and y is equal to k will affect only s, not t. Initial conditions on t will be used at the end. This is always the case, right? So now we have another PDE in two variables now. From three variables, we have converted this to two variables. So sxx plus syy minus lambda s equal to 0. So x goes from 0 to L and y goes from 0 to k. There is no t now. All right. So boundary conditions are s at 0, y 0, and s at ly 0, and s at x0 is equal to 0, and s at xk equal to 0. So these are the two conditions for x is equal to 0 and x equal to L, and these are the two conditions for y0 and yk. So this is true for all x, this is true for all y. Initial conditions I'm not writing. So this is a two, I have four derivatives here, four initial conditions here, so we boundary conditions here. So we are okay. So now again we will separate this x and y. Now assume sxy equal to x of x and y of y. As we have already separated the variable t, now we have only two variables which are still together in the form of PDE. So I can separate now x and y as well. So your PDE, let's call it 2. All right. This gives you sxx means x double prime and y as it is, plus syy means x as it is, y double prime, minus lambda s is xy equal to 0. All right. So now divide by xy, divide by xy, you will get x double prime by x, y double prime by y, minus lambda equal to 0. So now you see you have, this is x only and this is y only. So you can bring one of these variables to the right hand side. You will get x double prime by x equal to minus y double prime by y plus lambda. Now you see here you have x only, here you have y only. So this is equal to another constant, let's call it minus mu. All right. So again this will be a constant and I can call it negative mu now. In our equation it was plus. So let me correct this. This was plus, so this is plus, this is plus. So this is minus equal to minus mu. Now from here, x double prime by x will be equal to minus mu, and y double prime by y plus lambda will be equal to mu. All right. So from here you got x double prime plus mu x equal to 0, and y double prime plus lambda minus mu y is equal to 0. So now I got two ODEs. You see, two more seconds. Now everything is separated. X and y both are separated. Now if I use these conditions, s at 0, y is equal to 0 will give me x 0 0. This will give me x at L equal to 0. All right. So you are of course master in this now. So x at 0 is equal to 0. X at L is equal to 0. You have to show this by taking this. S at 0, y means x at 0, y of y is equal to 0. So it means x of 0 has to be equal to 0. Similarly, the other three will give you this one. So y at 0 is equal to 0, and y at k is equal to 0. All right. So now see, these both are the same boundary value problems with the same initial conditions. Here, because I have just one eigenvalue mu, so I can solve it first. I will get mu from here and plug that mu here, and then I will solve for lambda. So I'll get both the values lambda as well as mu. All right. So first solve this boundary value problem. So this boundary value problem, and as this is very well known now, we have solved it many times. So I will again not spend too much time on this one. This clearly gives that, sorry, this was mu. So this clearly gives that mu n is equal to n pi by L square, and your xn of x, your eigenfunctions are sine n pi by L x, and n goes from 1 to 3. 0 is not included in this case, right? Similarly, now if I go to the other thing, y double prime plus lambda minus mu. My mu is known. All right. Mu is known now. N pi by L square, y is equal to 0. Y at 0 is equal to 0, and y at k is equal to 0. Now this again will have the solution as, now this is your whole thing is your eigenvalue. So it means lambda m minus n pi by L square should be equal to m pi by k. Because I have already used n subscript for this one, so I have to use a separate subscript now. Let's say lambda m. All right. This should be equal to mk square. Yn of y is equal to, and again we have same boundary conditions, and as we have same boundary conditions, so my eigenfunctions will still be sine m pi by k square x y, and this is again n goes from 1 to, sorry, m goes from 1 to 3 and so on. So lambda m is basically m pi by k square plus n pi by L square. So you can, because I need the value of lambda, so you can bring it to the other side and write lambda. So if I write this lambda as n pi by L square plus m pi by k square, all right, then it is more appropriate to write this as nm, because I'm having two index sets here, n and m. Both n and m goes from 1 to up to infinity. All right. So it means it's better to write lambda nm, because we are getting, for different n and m, we are getting different lambdas. So just one subscript lambda m will not be enough. All right. So your solution for this whole equation, Sxy, which is equal to product of x and yn, I can write, so therefore I can write Snm xy is equal to xn x and y m y. So this is equal to sine n pi by Lx and sine m pi by k y. So this is your solution. Again, n and m, so lambda is this, where lambda is equal to this one. Again, n goes from 1 to 3 and so on. Now your ODE for t is t double prime plus c square lambda t. This was your ODE for t. All right. Now lambda is known to me, so this will become c square lambda nmt. These are given values of lambda. And now from here, your auxiliary equation is m square is equal to minus c square lambda nm. So you will get m is equal to plus minus iota square root of lambda n m. All right. So therefore, your t of t is equal to c1 cosine c square root of lambda n m t plus c2 sine c square root of lambda n m t. So this is what you got. We don't have any homogeneous initial conditions here, so we cannot use it. I will write the final answer. So therefore, the product solution uxt will be, therefore, u n m x t x y t will be equal to s n m x y and t of t. This is what you will get. So your u n m x y t becomes sine n pi by lx sine m pi by ky times, because we have two subscripts here n and m, so I will have to write a n m cosine c square root of lambda n m t plus b n m sine c square root of lambda n m t. This is our solution. So therefore the general solution will be, the general solution is u of x y t, and that is nothing but the sum, and there will be two sums because I have two subscripts s n and m, so I have to add both of them. So n will go from 1 to infinity, m will go from 1 to infinity. All right. So this is your general solution. I can write it in terms of sine cosine. Sine n pi l by x, m pi by k y, and a n m cosine c lambda n m t plus b n m sine c n m t. So this is your general solution. Now we have two unknown coefficients still standing there, a n m and b n m. So what we can do is we can use initial conditions, because there are two initial conditions still left. I can use them to obtain the values. So uxy0 is equal to fxy. All right. So fxy is equal to the value of u at 0, cosine 0 1 sine 0 0. So you got summation m goes from 1 to infinity, n goes from 1 to infinity, a n m sine n pi by lx and sine m pi by ky. This is a double Fourier series, you see. We are having sine, but there are two sines here. So what we can do is we can write this. Now you see, if I treat this as one thing constant, if I name it, then this is just a Fourier sine series in y. This is just a Fourier sine series in y. All right. What I can do is I can write the coefficient, this coefficient, right? Let's treat this as a coefficient. So this coefficient will be equal to integral from 0 to k. What we do is, whatever function we have, we multiply by this term, which is sine m by k y dy, 2 by k is equal to, the coefficient for that is this whole thing. So this is your coefficient. Right? And now you see, this is again a Fourier sine series. So these will, so now I will treat this whole thing as a function. This is a function of x only. All right. This is just h of x, let's say. This is a function of x. So what we do is we multiply this hx by this sign and integrate to get a and m. All right. So from here, your a and m will be equal to your hx times sine n pi by lx dx, and x goes from 0 to L and 2 by L outside. Now, what is h of x? H of x is 2 by L, 0 to L. H of x was already an integral. It was 2 by k. So this will become 4 by Lk. And integral from 0 to k, fxy sine m pi by k y, and now we have sine n pi by Lx dy dx. dy dx. So now see, this is a double integration. We got a double integration to get a and m. All right, so this is one of the coefficients. Second initial condition is ut at xy0 is equal to g of xy. So g of xy will be equal to the derivative at t is equal to 0. The derivative at t is equal to 0 of this equation is derivative with respect to t. So with respect to t, this will become sine, and sine 0 is 0. This will become cosine, and cosine 0 is 1. So I will get b and m. But with that, this is also your coefficient. B and m, c square root of lambda and m as well. So you got summation n goes from 1 to infinity, n goes from 1 to infinity, b and m, but you have c square root of lambda and m with it as well, because it is coming from the derivative, and sine n pi by lx sine m pi by k y. So again, this is a double Fourier series. So by following this formula, only difference is it is the exact same series. You see, this is the exact same series. This series and this series is exactly the same. Only difference is instead of a and m, you are getting this b and m. So following the same steps, b and m times c square root of lambda and m, because this is your coefficient now. This will be equal to 4 by lk, 0 to L, 0 to k. Instead of g, x, we have g, and now sine m pi by k y. You can write anything first. You can write sine first, cosine first. Nothing will change because it doesn't matter. It's a multiplication. Only difference is this thing should not be changed. You see, the first integral is with respect to y. The second integration is with respect to L. This is important. Doesn't matter if you are writing sine x first and sine phi later, will not change anything. So from here, your b and m is 4 divided by CLK square root of lambda and m, 0 to L, 0 to k, g of xy sine m pi by k y, and sine n pi by L x dy dx. So this is your b and m. All right, so that's how we got a and m and b and m by using initial condition. So this is your complete solution of the second, this is your complete solution of the wave equation in 2 dimensions. So basically in 3 variables. Wave equation in x, y, and t is in 3 variables. So this was a very extensive example, very thorough example of how we can solve a PDE with the separation of variables technique for more than 2 variables. 2 variables were easy, but in 3 variables we have to separate 1 variable first, then you will get a PDE in 2 variables, and then I will again use the method of separation to separate those 2 variables as well. And at the end we can multiply all together. All right? So this was your second dimensional wave equation in 3 variables x, y, t with respect to the homogeneous boundary conditions and given non-homogeneous initial conditions. So we completely solved it. Let's do one more example where you are given a circular membrane, right? Instead, if you look at this 2-dimensional body of this type is defined in polar coordinates by r between 0 and alpha, and theta goes from minus pi to pi. If the body force is negligible and the boundary r is equal to alpha is fixed, then the vertical vibration of the membrane are described by the initial boundary value problem this. The right hand side, as we have mentioned before in the Laplace equation, if you recall, the Laplacian in two-dimensional is given by this one. If xy is replaced by r theta, then your uxx plus uyy will be changed to urr plus 1 over ur plus 1 over r square u theta theta, and utt will remain as it is. All right. So now r is between 0 and alpha, theta is between minus pi, and t is positive. Again, only boundary condition is given that u at alpha is defined, that u at alpha theta t is equal to 0. This is the only boundary condition given to you. Other conditions are that at r is equal to 0, your u will be bounded, and these are the periodic boundary conditions, that because we are starting from minus pi and ending up at the same point, so at that point u at minus pi and plus pi should be the same. The derivative at minus pi and pi should be the same as well. So, and initial conditions are given to you, that ur theta 0 is given, ut at r theta 0 is also given to you. So how we can solve this equation? All right. So let's solve this equation by separation of variables. So wave equation in a circular membrane. utt is equal to c square urr plus 1 over r ur plus 1 over r square u theta theta. All right. So r is between 0 and alpha, theta is between minus pi to pi, and t is of course positive. Boundary conditions is only one condition, that u at alpha theta t. At r is equal to alpha, it is 0. Basically now you have a circular membrane, right? Circular membrane in 2D. So this is what you are having. So at this is r is equal to alpha, the boundary. So at boundary it is 0, displacement is 0, that is the boundary is fixed basically, and now you are beating this drum. Usually if you look at the drum is the circular membrane, and you hit the drum, there will be vibrations. Those vibrations are calculated from this two-dimensional wave equation in a circular membrane, and at r is equal to 0, at this point your u should be bounded, right? It can go to infinity, but because vibrations will not go to infinity. Doesn't matter how hard you hit the drum. Of course, there will be finite vibrations. So u 0 theta t is bounded. This is your boundedness condition. Periodic boundary conditions are u at minus pi t is equal to u at r pi t, right? And u theta r minus pi t, the same as u theta r pi t. So at this point, this is minus pi and pi. At this point, your u should be the same and your derivative of u should be the same. And initial conditions are given as u r theta 0 is f r theta, and u r theta ut r theta 0 is g r theta. So this is the complete boundary value problem, initial boundary value problem for a circular membrane. So again, what we will do is we will assume the solution of the form u r theta t is equal to, so again u r theta t should be equal to s r theta and t of t. So we are separating the t variable first. So your PDE 1, let's call this PDE 1. So PDE 1 gives utt, so s as it is, second derivative of time, is equal to c square urr, so s r r t plus 1 over r s r t plus 1 over r square s theta theta t. So now if I divide by st, c square st, I want to get rid of this c square from the right hand side. You will get t double prime over c square t is equal to srr plus 1 over r sr plus 1 over r square s theta theta divided by s, right? Because t will be cancelled and c square is also cancelled. So here you got only t, here you got only r theta, right? So it means this should be equal to a constant which is minus lambda. So t double prime plus c square t lambda t is equal to 0. This is your ODE for t. So we have separated the t variable, but from here you will get another PDE SRR plus 1 over R SR plus 1 over R square S theta theta plus lambda S is equal to 0. Alright, this is plus lambda S because S will be multiplied here and you can bring it to the left. Boundary conditions again will become, because you see here, what is the boundary condition? U at alpha theta t. So S at alpha theta is equal to 0, right? So this will become S at R is equal to alpha and theta will remain theta is equal to 0. Second is S at 0 theta is bounded, right? And S at R as it is theta minus pi should be equal to SR pi. That are the periodic boundary conditions, and if you work with them a little bit you will get these. Because we have enough practice with this now, so I'm not wasting my time. You can easily do this. Alright, so you can verify all these boundary conditions. You will get these boundary conditions. Alright, now again assume the solution of the form that S R theta R of R and capital theta of theta. Alright, so let's say we can write it as this. Then this PDE 2. Then PDE 2 gives S or R means R double prime. Now you can write R double prime because R is a function of only one variable R. R double prime theta as it is plus 1 over R, R prime theta as it is plus 1 over R square, R as it is theta double prime plus lambda R theta is equal to 0. So again if you divide by R theta, so divide by R theta, what you will get, theta will be cancelled from first two terms, here R will be cancelled. Alright, so you will get R double prime by R plus 1 over R, R prime by R, and then plus 1 over R square theta double prime over theta because R will be cancelled, and plus lambda is equal to 0. Alright, now if you multiply by R square you will get R square R double prime by R plus R prime by R, and lambda will have R square, so I can write plus lambda R square, and this will have nothing, so I can send this on the right hand side. Now you see on the left hand side you have R only, on the right hand side you have theta only, so this should be equal to mu, so I can call it mu. So the reason I'm calling it mu is with negative sign here, if I put negative sign here as well, I will get theta double prime minus mu theta is equal to 0. But we have been solving x double prime plus lambda x equal to 0. So just to make this of that shape, I'm not putting minus sign here. Alright. So now you will get two ODEs, R double prime plus R prime plus lambda R square minus mu R is equal to 0. This is an ODE for R. ODE for R, and now ODE for theta is theta double prime plus mu theta is equal to 0. So this is that usual ODE which we have been solving. So this is an ODE for theta. All right, so I can solve this first before that, because here I have just one mu. So it's better to solve this first and get the mu, put it here, and then solve it for lambda. So boundary conditions will be changed like this. S alpha theta is equal to 0 means R at alpha is equal to 0, right? S 0 theta is bounded means R at 0 should be bounded. Similarly, the periodic boundary conditions minus pi to pi, this implies that theta at minus pi is the same as theta at pi, and similarly S theta R minus pi, S theta R pi will give you theta with respect to theta minus pi is the same as theta with respect to theta pi. All right, so these are the boundary conditions. So therefore what we have is, we got theta double prime plus mu theta is equal to 0 subject to the periodic boundary condition. Boundary condition on theta are periodic, right? And theta at minus pi is equal to theta at pi, and you know that we have been solving this thing, and mu of n is nothing but again n pi by L square, but in our case L is pi, so n pi by pi square, that is eventually n square only. All right, so mu n is n square, and your eigenfunctions were sine and cosine, right? Eigenfunctions were cosine n theta, sine n theta. These were your eigenfunctions. So what you can say is, for 0, theta 0 of theta is just 1, theta 1 n is cosine n theta, and theta 2 n is sine n theta. All right, for n is equal to 0, you are only getting one function, but for n is equal to 1, 2, 3, you are getting two eigenfunctions, not just one. All right, so n goes from 0, 1, 2, and so on. These are your eigenvalues. Now the next one is Cauchy-Euler equation, R double prime. So if you move on to Cauchy-Euler equation, you got, now we have R square R double prime plus RR plus lambda R square minus mu n, because mu is known to me now, mu n is known, mu n R is equal to 0. This is not a Cauchy-Euler equation. This is because for Cauchy-Euler equation we should not have this a function of R. This should be a constant. Here it depends on R. So this is not a Cauchy-Euler equation. This is a well-known equation called a Bessel equation. Mu n is n square, so I can replace the value here. Okay, this is a special kind of ODE, which is Bessel equation, but Bessel equation has just x square here, or variable square, no lambda. All right, so if we set, we will discuss in next lectures, we will discuss Bessel equations in great detail. So right now I am just giving you the idea what Bessel equation is and what are their solutions. In next lecture we will be proving how we get these solutions. So right now, if you have not heard about Bessel equations, you don't have to worry about it. We'll come back to it later. So if I set this lambda r square or xi is equal to square root of lambda r, then this becomes xi square. All right, let's call this transformation lambda r, and let's say what will your r becomes. R of r will become r is xi by square root of lambda. Square root of lambda is constant, so this is a function of xi. So I can call it, let's say, psi of xi. I'm just renaming r in terms of xi by lambda will be called psi. Then this equation, this equation 3 will become xi square psi double prime of xi plus xi psi prime of xi plus xi square minus n square xi is equal to 0. This is actually the Bessel equation of order n. This is a Bessel equation of order n. Order n here is different than the order of the differential equation. N is basically a parameter here, so if you take n0, I'll call it a Bessel equation of order 0, n1 Bessel equation of order 1, and so on. Actually, these all equations of second order differential equation. That order of differential equation is 2 because phi double prime. Here, Bessel equation, if I write Bessel equation of order 3, it is understood that we are taking n is equal to 3. Order of the equation remains 2. All right? And this has a solution. This is a Bessel's equation of order n, which has two linearly independent solutions, Jn and Yn of x, Jn of xi and Yn of xi. These are the two equations. These are called Bessel functions because they are the solutions of Bessel equation. That's why we call them Bessel functions of first and second kind of order n. Again, order n is coming from this subscript small n. All right. So these are the Bessel functions of order n of first kind and second kind. And as I said, we will come back to it. So we will be proving these values, but right now I'm just writing. It is well known that for small xi, that is in the limit as xi goes to 0, our Bessel functions can be written as this. They are approximately equal to 1 if n is 0 and 1 over 2n n factorial xi n. This is the case when n is equal to 0, and this is the case. So n positive, not equal to 0 means positive. And yn of x xi is almost equal to 2 by pi natural log of xi if n is not equal to 0, and 2n n minus 1 factorial over pi minus n when n is positive. All right, so these two are the functions when your xi is small. All right, if xi is not small, then they have a bigger expression. So we will be proving them later on, so don't worry about it. Right now, I'm just writing them just to fulfill our needs. So therefore, your R of R should be equal to C1n Jn. Rn is C1n Jn square root of lambda r plus C2n Yn square root of lambda r, right? This is your solution for the Rn, but this Y2n is not bounded. This goes to infinity as r goes to 0. All right, so this means we have to take Cn equal to 0 to keep r bounded. You know that we have the condition that r at 0 should be bounded. This becomes infinity as r goes to 0. So I have to make this thing equal to 0 to get rid of this unbounded part. So get rid of unbounded part and keep only the bounded part of r, which is just C1n Jn square root of lambda r. All right. Also, we have a condition that Rn at 0 at alpha is equal to 0. This was the boundary condition. This implies that Jn square root of lambda alpha is equal to 0. All right. And now we don't know how many zeros are there, right? We don't know how many zeros are there. So let's call them lambda alpha is equal to xi and m. Let's call them the zeros. Let's call them the zeros of your equation. All right, m goes from 1, 2, and so on. and then lambda nm will be xi nm by alpha square. So these are your values where xi nm are the zeros of Bessel functions of order m, 1, 2, so on. So what will be your Rnm then? Rnm of R is equal to Jn, and lambda is, square root of lambda is xi nm by alpha R. So these are your solutions, all the solutions. Note that these Jn are also orthogonal functions, are orthogonal to each other, but they are orthogonal with respect to the weight function R. Sine and cosine are orthogonal with respect to weight function 1, but here we need to multiply by R to get the integral 0. So here weight function is not 1, but it's R. So I can write the final solution as, if I write u nm r theta t, that will be equal to x r and theta m and theta, right, and t of t. So we have Bessel functions here for R. We have Jn xi nm by alpha R. Our theta was a nm cosine n theta plus b nm sine n theta, and our t was c1 cosine xi nm by alpha ct plus c2 sine xi mn by alpha ct. So this will be your product solution. Then we will have to sum it up to get the final solution. Your initial condition is u r theta 0 is equal to f, and u t r theta 0 is equal to g. All right. So if one of them is 0, maybe you can simplify this thing and one of them can cancel out. All right. Let's say if ut at r theta 0 is equal to 0, let's say g r theta is equal to 0, then what will happen? This sine term will drop out, because the derivative of sine is cosine, cosine 0 is 1, so c2 will become 0. So if it's not, then of course we have this general big solution. All right. So therefore the final solution u r theta t is nothing but the sum over all the values. N goes from 0 to infinity, m goes from 1 to infinity, and this is u n m r theta t. So if you sum them up over all m and m, you will get a solution. And of course the initial conditions can be used. U r theta 0 is equal to summation u n m r theta 0. So of course r theta 0 cosine 0 is 1 and sine 0 is 0. So you will be left with only series of this form a n m cosine n theta plus b n m sine n theta, and then you will have j n of xi n m by alpha r, and cosine 0 is 1. So sine 0 0, cosine 0 is 1, so this is your summation. So that is your fr theta. So again, it's a Fourier series, double series in cosine, sine, and then j. Because all of them are orthogonal, you can use the orthogonality to find a n m and b n m. All right, it's very easy if you can find them. So we can use the orthogonality of Jn and then the orthogonality of sine cosine to obtain a n m and b n m as before. So we have been doing this for quite a time now. It's not a problem. All right. So we know how to find the coefficients, Fourier coefficients A&M and B&M by just multiplying the function with the multiplying the eigenfunction with the given function and integrating. It will get rid of the function on the right hand side. Then you will be left with sine and cosine. Again, you will multiply by cosine and sine to get the values of A and M and B and M. So we have solved this wave equation in a circular membrane subject to the given boundary and initial conditions, and these three conditions are built-in conditions. We have to use them to get the final solution. So when you solve a wave equation in 2 dimensions, you get Bessel equations for R. So we need a theory of Bessel equations to really solve it. We will be coming to that Bessel equation, and we will do them in great detail. So right now we just use the solution, we just use the knowledge that the Bessel equation has the solution Jn and Yn, and to keep the solutions bounded, we just kept Jn and ignored Yn part of the solutions. So today we did the separation of variable technique for more than 2 variables, equations involving more than 2 variables. So this is it for today's lecture. We solved 2 examples, very extensive example, one in rectangular membrane, the other in circular membrane. So one in Cartesian coordinates, the other in polar coordinates. All right, I hope you understood this technique well for more than 2 variables as well now. With that, I will thank you for being with me for the whole lecture, and I'll see you in the next lecture. Till then, Allah Hafiz and Assalamu Alaikum.